Well, good morning or good afternoon, whenever it is you're watching this video. We're going to start Unit 3 now in General Chemistry, and Unit 3 is going to cover the periodic table. Now, the periodic table has a lot to it. Of course, we've already started learning some of the names and the symbols of the elements of the periodic table, but also we need to talk about the atom itself, and so that's where we're going to start. We're going to focus on the atom. And really, the idea of what an atom actually is a fairly new concept. And we're going to see that in this video. This is going to be video 3.1, the history of the atomic model. So first we have Aristotle. Now, Aristotle isn't what we would consider a scientist by today's means, but in his time, he is the one who would have used logic and reasoning and reasonable explanations to describe the matter and the world around him. And so Aristotle's idea of what matter consisted of was basically the four elements that many people thought for long times that's how matter was made: earth, water, wind, and fire. Now, you might say, well, we know that water is not an element. By now, here in general chemistry, we know that water is a compound, right? H2O. Well, at that time, they didn't know that water was composed of two hydrogens and one oxygen. And so what they did was they looked at something and said, okay, there's a stick of wood. Let's see what's making up that stick of wood. Well, if it burns, it must have contained fire. And if they look and watch very closely, they'll notice that steam also comes out of the fire. Well, there must have been water in the wood as well. And what's left when you burn a piece of wood? Ash, right? Looks like dirt. So they said, well, there must be earth, some amount of earth inside that wood as well. Well, doesn't the heat rise and you feel the wind moving off the fire? Well, there was also some wind in that stick of wood. So in some combination of things, there must have been some earth, some water, some wind, and some fire. And for thousands of years, really, that's the way people described matter. They said that it had to have either one or more of these things in it to be considered matter. In the 1700s, a scientist named Dalton comes along, and he doesn't have any scanning electron microscopes by this time. I mean, it's the 1700s. We don't have electron microscopes until the mid to late 1900s. But Dalton talked about matter, and he theorized that atoms, the things that made up matter, were small, indestructible solid masses. And we call those the billiard ball models. Now, you might call it pool balls, but at the time the game was called billiards. And a billiard ball is a solid, hard ball. It's incompressible. It is it's round, it's smooth, and that's what he based his model on. Dalton thought that atoms were small billiard balls. The only difference between one type of matter and another type of matter then was the mass. So that's what he thought atoms were small little solid particles. And you can see this too in your book on page 66. Thomson is the one who discovered the electrons. He realized that Dalton's model of small little indestructible masses wasn't entirely correct. Now, he did say that they're small, he did say that they have mass, but he discovered little negative charges on the atom. And so he had to modify the model in order to fit his new information. And so in his day, one of the best desserts that you could have would be plum pudding. And plum pudding is a pudding base that has raisins all stuck through it. So he said his model of the atom is going to be like a bowl of pudding, still a round mass of pudding, but it's got these little raisins, these little negative charges stuck randomly through it into this lump, the pudding mass. Now, I didn't talk anything about neutrons, didn't say anything about protons, didn't talk about quantities of things. It's still based one type of matter, compared one type of matter to another based on the mass. Next is Rutherford. And Rutherford's contribution is rather unique because Rutherford discovered something else. Thomson's model, which worked off Dalton's model, said it wasn't just a solid mass, it was a mushy mass with these little negative particles stuck in it. Well, Rutherford discovered that it's not a mass at all of a pudding or a solid thing. It's mostly empty space. But he did discover that there is something solid at the center of the atom. This is Rutherford's gold foil experiment. It has an alpha particle emitter. This is a little radioactive substance that emits a little stream of alpha particles out this one little pinhole, and there is a gold foil, piece of gold foil right here, only a couple of atoms thick. Around it is a screen that is coated with a phosphorescent material so that wherever the radiation touches, it's going to glow, and he expects the radiation to go straight through and make a glowing dot on the other side. But when he started the radiation and pointed it at the gold foil, he didn't just get one dot here, which he did get one dot, but he got a dot here, and a dot there, and a dot over here, and over here, and over there. This is Rutherford's gold foil experiment very close up. It shows that the gold foil was only a few atoms thick. Now the alpha particles, radioactive particles, come flying in very fast, and he expected them to go straight on through and impact with the screen on the other side, showing a bright dot over there. But what he saw were bright dots all around the screen, meaning that the alpha particles that are coming in are not going straight through, they are impacting with something inside the atoms. That something was the nucleus. The nucleus is what Rutherford discovered through his gold foil experiment, and we'll talk more about it soon. Now, Niels Bohr is the one that took these other models. By now, we pretty much know they're not solid little balls like Dalton's model. We know they're not just plum pudding models like Thomson's model, because there's more to it than just these little negative charges. Bohr proposed that, yes, there is a small little nucleus, but these little negative charges that were on the outside don't just sit there. They travel around the nucleus in specific paths. And so the Bohr model is said to have quantified what's going on with the electrons, where they are, how many of them there are, and he talked about energy levels. The Bohr model is traditionally what we would think of when we're talking about an atom. If you watch a cartoon, you're going to see a little atom with the electrons spinning around them in various orbits. That is the Bohr model. It's not entirely correct, but it was one of those models in the path of all the different models that lead us up to what we believe atoms are today. So we have an energy level. An energy level is that region around the nucleus where those electrons might travel. It's that path. That would be an energy level. And a quantum. Bohr theorized that a quantum of energy was required to get one of these little guys, one of these little electrons, to jump from its level to a higher level. And if it jumps to a higher level, we say that electron is at excited state of energy. But this is the Bohr model. All right, in the early 1900s, Schrödinger, and there were some others that worked with him, but Schrödinger is the one who gave us what we call the quantum model. He took the equations that they were working with to try to explain what was going on with the electrons and realized that these equations didn't really work all the time. The problem is an electron doesn't always travel in this nice, neat little path around the model like the Bohr model suggested. Schrödinger said that we can't really understand where the electron really is. And another gentleman by the name of Heisenberg is the one who came up with an uncertainty principle. The Heisenberg uncertainty principle says that we really can't know where the electron is all the time because, as Mr. Schrödinger said, the electron is really behaving not just as a particle, as you see it here, but it's behaving as a wave, too. And that's called the dual nature of the electron. An electron can behave as a particle an electron behaves as a wave at the same time. That's why it's hard to explain what's going on. But the electrons are so small anyway that it's one of those mysteries, and we really don't even see electrons. We can see some atoms, but we can't see the individual electrons. For one, they're so small, but also because Schrödinger and Heisenberg correctly theorized that we don't know where they are. We can guess where they are probably going to be, but we can't say for sure because they're traveling at the speed of light. They're so tiny, they're behaving as waves and particles at the same time that we really can't predict where they are. The places that these electrons would probably live are called orbitals. Instead of orbit levels or energy levels, now we're talking about atomic orbitals, the regions of space where there's a high probability of finding an electron. And there are some shapes that we're going to talk about too. S, P, D, and F shaped orbitals. To kind of round everything out, in 1932, a doctor named Chadwick discovered the neutrons. He finally understood and explained why there was some missing mass in the atom. We know that there's mass in the protons, which we talked about, the positive charge. We know there's no mass in the electrons, and they're not even included in the mass. But there was some missing mass. And so in 1932, Chadwick theorized and proved that there's another particle in the nucleus, and he called it the neutron. It's neutral, so they are neutrons. And this completed what we call the quantum mechanical model of the atom that we use today. Okay, I hope that explains some of what we're going to begin looking at in the atom. You see where we came from, where we're going to. We work today with the quantum mechanical model of the atom. We don't use the Bohr model. We don't go back and talk about the four basic elements, earth, water, wind, and fire. We use the quantum mechanical model of the atom. That's why it's so difficult to use sometimes, but that's the way it is.